Hello everyone. So I got my new microphone, so hopefully this sounds better. We'll see how that works. Hello everyone. So I got my new microphone, so hopefully... Okay. Alright, I was just checking to see how that works. Alright, so let me start in here. Hopefully there aren't any problems with the assignment. All right, so the first thing I want to talk about today. All right. Maybe get a drink here. All right, so the first thing. Good afternoon. Oh, afternoon. Well, it's 7 p.m., so I call that evening, but that's fine. That works. Good afternoon. All right, so all right. So I want to talk a little bit more about the floating point that we looked at. So we did a conversion. We did a real simple conversion of a floating point number. So I'm going to do another one here in a little bit, but I'm not going to do it right away. And you'll understand, I think, hopefully when we get to it. All right, so what I want to do to start off with here is I want to talk about the IEEE, an IEEE standard. Remember what IEEE was? That's our electrical and electronics engineers. So they have a standard called 754. This is their version of floating points. And it's pretty standard now. Floating point. I did check out that website, by the way, with the, what is it? Everything. Where's my note? Notes are under somewhere. Oh, there we go. Explain everything. So that, I think it would work. I can't save from there. It didn't look like I could save very easily from there. And I think I have a workaround to work through here anyways. There's this little thing called insert space, which has kind of been my frustration. If you'll notice, I've already used that and inserted a bunch of space here so that I can get it all on one page. And that's the reason why Lecture 5's notes aren't up there yet, because I had to combine those PDFs. So I'll get that done here tonight, after today's class. Okay, so they use the exact same things that we talked about before. They have one sign bit, and then they have 8 exponents. Bits and 23 significance. Significance. So, significant bits. For a grand total of 32. Most modern computers are 64 bits. So you can do 2 floating points on the same line. Now, this is single precision. If you go for double precision, it would be 64, and everything. Well, the sign bit doesn't double. I'm not sure where the numbers line up on double precision. We'll talk about why we do that. Why we would maybe use a double, And in fact, actually, if you're used to doing floating point things in Java, you'll usually, if you're going to use a floating point, you're going to use a double. Okay. Not always, and we'll talk about why that is, actually, even. Okay. So their just numbers are a little bit different. All right, so I'm going to use what they've got, and I'm going to talk about three things here. And that is range. So that'll be number one. So range is the same as it would be in a mathematics formula or not number, but variable, in that this is the highest value, highest possible value. I'm not going to put positive there, but the highest value minus the lowest value. Or another way to say it is what, not necessarily minus, because that just gives you the total breadth of the situation, I guess. That's a different word. So it's not minus. It's, I put a little caret in here. 2. And we can state it either highest or lowest. So in 32-bit floating, with an 8 bits of for the exponent, and remember we've got this bias, right? So in this case, the bias is a 0 followed by 7 ones. So then the range is 2. Well, right, because it's 2. So the 8th bit would be 256. So to 256. Oh, is that right? Yeah, 256. Nope, because it's 7. Whoa, that was weird. That's really weird. Okay, I've got all kinds of stuff going on now. Hitting keys I don't mean to hit. All right. Guess I get to write that highest to lowest value. And we're going to erase it. And actually, we're just going to look it up because, we can do that. Let's bring this over here, and what are we going to get? So we get IEEE-754. Floating point. Incidentally, okay, so this is actually a great spot to talk about this. This is the first spot that we've run into it. Is Wikipedia a good source for what we're doing? That's an interesting question, isn't it? A lot of people will say Wikipedia is not a good source. It's not a good place to go to get information about things. And I would agree completely on anything that's contentious. But anything that's not contentious, so even some things in history, right? Like, I don't know, there are constantly, not constantly, there are things that are even very, very old that are controversial as far as history goes. But just because the records, sometimes it's because of records, sometimes there's conflicting records or otherwise. And so anything that's contested at all, but in this case, right, it's a definition of of a method to do floating point. Well, this is floating point arithmetic. So in this case, there's not really a lot of motivation for people to go in and change it to something that's non-factual. So, trust it to a certain extent because it is a wiki, but it's probably just as good as any other encyclopedia. That's my opinion on things. I would not use it for any kind of political thing at all, period, even if it's very old. So that just because people tend to change things because they're not agreeing with everyone else. So, but in this case, perfectly fine. Most mathematics stuff, I don't think has any controversy with it, for the most part. If there is, it's friendly controversy. So, all right. So let's look here. Does it tell us what the range is? There's some specialty things. Actually, two kinds of non-numbers. There's a quiet one and a signaled one. Yeah, and actually we could look at a table. I think the book has a table that talks about it. Oh, actually, that's what I can do. I can look here. That doesn't help. Oh, actually, the range is, so let's go back here, positive 3,207.68 to negative 32,700. Oh, I got something wrong. Because anytime you do this, you always will have a disparity. Because you have to have 0, right? One of the numbers has to be 0. So in this case, and in most cases, because of the way 2's complement works, or in this case, the bias works, this is the range. This is our range. So it just tells us the different possible values that we can put in there for the base 2, right? So 2 to the blah, 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 one of these two. Either positive 32,767 or negative 32,768. So and those are fairly either this pretty big, right? So let me actually, let's go back here, and there's just 2, actually exponent calculator, 2 raised to the 32,767th power. Oops, messed that up. We need to hit the equal sign. Hit enter. Go on. It crashed out. It wouldn't handle it. It's too big. Yeah. That's... Oh, this is for an int? Oh, yeah, that's right. That's the same for an int, actually. It's not going to give us that calculator. Two caret 3,206.70. No. What was it? What did I write down here? 767. 767. Close that. Equal sign. Boy, it will not. It just does not want to work for us. That's all right. Well, It's a big number, by the way. This is actually a very, very big number. So we'll just go with, it's big. So, oh no, this isn't for the IEEE one. I misspoke on this. This isn't not correct. Actually, it's far bigger than this. This is the maximum range in an integer, 2's complement integer. I don't need this. This is a 2's complement integer. It gives us a range. If we looked at the exponent range, it would be 2 to the, well, whatever would be, the positives would be 7 ones, a 0 followed by 7 ones. So that would be, I think this might be the right number. No, it's not. No, right, this isn't. It's 2 to the 255 to negative 2 to the 250. Oh, actually, it's not 255, it's 256. 256 minus 1. This is the exponent. So that's the exponent of IEEE dash 754. That's the range there. And we could say the range here because now the significant bits are never going to be negative. They're always positive. And so, right, we have a sign bit, so we don't actually, right, that's not, man, I messed this up. That's negative. So it's a really fairly small number. That's a very small number. So one of the ways to convert, actually, every time you take off of 10, so you subtract 10 from this exponent, it's like adding 3 zeros to the number on base 10. So we could say this is 25 times 3 or 75. So this, actually, this is kind of a neat thing. So 256. So then we could take 2 to the 6th power. And what is 2 to the 6th power? 2 to the 6th power is 128. So this roughly equals 128, which represents 2 to the 6th. And then we have this 250. And so 25 times. So times 10 to the 75th. Because it's times, you add 3 zeros each time. So it's 128 followed by 75 zeros. That's a big enough number. I don't think we're too worried about running out of space with that one. And then we can go in the negative direction, the exact same number of same distance. So it's pretty good. Okay. So the range on this is quite good. Okay. So then that was range. Now the next one is accuracy. No, sorry, not accuracy. That'll be the third one. The second one is precision. So the way to think about precision is if we go up here to the significant bits, we would say, well, how many are there that are important? How many are there that are non-zeros? And so we start counting from the left, right? So if we had something like this, 0, 1, 1, 0, 1, 0, and then we just had all bunches more zeros to fill out our 23, we would say in this case there's 1, 2, 3, 4, 5. 5 significant bits. And so that is the precision. Because we rounded at 5. Maybe we didn't round. Maybe we got it exactly on. But in any case, that 5 is the... And so if we changed the number a bit and made this bigger so that we could... And then multiplied this by... Or divided this by 2, or did it the other direction, right? So then we could say then that the significant number of bits would be 4. So this is really analogous. It's not exactly the same, but it's basically the number of significant. It's not a number, and that's the reason why. So if something is more precise than another thing, that means it has more significant digits. Basically, the amount of significant bits, or we can actually extend that to digits as well if we're in mathematics. Right, so if we're in base 10, we could say digits, because in that case a bit is the same as a digit, right? It's the same, it's just another character. Right, so if I was to ask 1.5 times 10 to the 7th and 2.25 times 10 to the 9th. Which one of these has a higher precision? Well, it's easy. The one that has more digits here. This has more digits. This is 3. This is 2. You can think of it that way. It's more precise because it has more digits. This is only it's a loose representation. And then the last one here is accuracy. So accuracy we can define as how close the representation is to the actual value. That'll make more sense. We're going to come back and revisit this in a second. Because we haven't really seen, there's a major flaw in floating point numbers, and we're going to see that here in a second. So how close is the representation? So if this was exactly right and we didn't have to do any rounding to get to this, this could be more precise than this one. We don't know, we can't know, not precise, more accurate. We can't know which one is more accurate until we know what the actual value each of them is trying to represent. Okay? That's very important to think about there. All right, let me give you an example, and I think this is going to make some sense here. Okay. I'm going to convert. We're going to kind of go back and do a little bit of review. 0.1 to a floating point. So I'm going to put that as FP. Okay, so how do we do that? How did we do that before? So we take the 0.1 and we multiply it by 2 and we get 0.2. And then we take that 0.2 and we multiply it, we get, 0.2. And we multiply this by 2 and we get 0.4. And then we multiply this by 2 again and we get 0.8. And, oops, not drawing the line. And then we multiply this by 2, and we're going to just keep going until we come to the end. And we're done, and we don't have any more numbers to deal with. So then this is 16. That'll be 1.6. All right, so now we're going to actually ignore this 1. We just ignore it. And so then we just take the 0.6 times 2, and I get 1.2. Okay, again, I'm going to ignore that 1 and go like that. So I get 0.4. Then I go ahead and multiply that, multiply that by 2 again, and I get 0. Make it better 0 than that. 0.8. Is anybody seeing a pattern? I am. We already had a 4 up here. We already had an 8 up here. Do you think it just looks like it's just going to keep repeating itself? Yes, it is going to keep repeating itself. So, this is what we do in order to do this. So then we start here and we go 1. We start with the dot. And then 1, 2, 3 zeros. And then 1, 1. And then 2 more zeros. And then we could say this part repeats. But if you look, it actually repeats like that. And we can erase these last 2 zeros. Because what's the next one going to be? It's going to be a 1. And then the one after that, going to be another 1. And then after that, be a 0 and a 0. And then it'll just keep repeating 2 zeros, 2 1s, 2 zeros, 2 1s. Okay, well, wait a second. Well, what do we do here? How do we figure this out? Well, if we're converting this into a floating point, and our example before, what did we use? 9 bits for the significant. And so we would actually put all 9 bits here, and then we would shift it over until that 1 was all the way in that first spot there. And then we would call that good, and that's called normalization, and then we would figure out how many decimal places we have to move, right? And then we would figure out our exponent and do that. But what's going to happen there? We're going to end up with extra bits that are off the screen somewheres. Right? So this would become 0.1100110001. Right? That gives the 1 in that first spot. And we could say that's times, well, we moved this over 3 times to get it to here. So 2 to the negative 3. So we would subtract 3 from 1. Not that important. But we would figure out that negative value to stick in there to make our significant, or to make our exponent. And then we would add our bias, and then that would get us a positive number. So it But what did we do with that extra stuff? Right? There's another 1 here. There's supposed to be a 1, and then a 0, and then a 0, and then a 1, and then that just keeps repeating. And we cut all that stuff off. Now, it's pretty insignificant, right? Because it's way out there. The value of this is actually quite small. It's something like 2 to the negative 10th, which is like 1 over 1,024, which, not that big of a deal. I guess I'm willing to sacrifice that being off by a little bit. Okay. Remember, our computer, at the very least, uses 23 bits of significant. That's with a single floating point. But it's probably a double. So that means there's going to be 23 bits here before we start cutting things off. So how close is 0.1 to actually being accurate? Pretty close, right? It's going to be 2 to the 24th, because that's the first one we're going to cut off. At the very least, right? And in this case, actually, will be a little bit little bit more than that even. 2 to the negative 24th before we can get any number that's off. Well, but it's still not 100% perfect. It's not 100% accurate. So floating point for some fractions, fractions as well, but some decimals is accurate. But for others, it is not. And actually, it turns out there's a way to kind of tell. Well, there's a way to tell when it's not. Or it can't be. And because in order for it to be I'm trying to remember. There's a way. I think it has to end in a 5 in order for it to be to terminate properly. But I could be wrong on that. I'm not 100% sure. Know that if I test you on this, when I test you on this, or when I give you an assignment, I will not give you one that doesn't terminate. However, I might ask you, why are floating point numbers not accurate? And you're going to want to be able to explain that. Right? Because we have to round. Because most decimals are not 100% accurate. Right? They're off a little bit. So accuracy, this is the error. Right? This is another way to think of it. This is the error. Precision is not a measure of error. It's a measure of how much representation that you actually have. So right in this case here, I could say, there are 9 bits of precision here. So, right, how much precision is it? Well, it's 9 bits of precision in base 2. Okay. That describes those two things. Yeah. Another problem with floating point numbers. We haven't done any math with floating point numbers, and it's a lot of stuff to keep track of. I'm not going to worry about you guys being able to do that necessarily by hand. Know that it is something that you will have to maybe do, or you should at least understand the concepts. So let's look here at math a little bit. So if we remember in some of our Foundations of Mathematics courses, if we've studied any of this, this is the associative. So the associative property in mathematics, right? So it says that any numbers that you take and add them together, if you're adding them together, it doesn't matter the order. I could also do the same thing with multiplication. Okay. This, not always true. True for floating points. Why is that? Because we have to throw things away sometimes. Because we can't remember everything. So we discard some of our significant bits. Because we're not sure, we always go to the lowest level of precision. Whichever one has the least precision becomes dominant. So if A has more precision than B, which has more precision than C, then this number has the total here would have a certain amount of significance. Or not significant, precision. And then here, we would have a different level of precision on this side, and that would give us a different level of precision in total. So that's part of the problem. Also, we have the accuracy problem is if in floating points, right? Because if the value itself is off, will the accuracy matter? Actually, the accuracy probably won't matter. But again, when we do arithmetic, addition, as long as the bases are the same, we'll be okay. But if the bases are different or requires a conversion while we do it, when we do the addition, then we are losing some precision and some accuracy. We might lose both. And so in any single addition problem, we might lose, would we always lose precision? It's possible to lose precision, actually, right? Because it's the number of significant, right? So, but if this gets pushed off the end and we have 3 zeros at the end, we can't count them. We would just have 6 bits of precision. So that's the reason why, that's part of the reason why. The other property that's a problem is the transitive problem, distribution problem. So A times B plus C in normal mathematics is equal to A times B plus A times C. This doesn't always true either. That's because in our addition, sometimes we throw things away differently. Also in our multiplication, we also sometimes lose some of that accuracy in different ways depending on the operation. Now, is this important for most things? The answer is no. And the reason is because, what's our range, right? Our range and and that kind of thing, right? We're talking a lot of significant bits, right? There's a lot of them there. So if we lose that one way out there at 23, at the 23rd spot, who cares, right? That's 2 to the negative 23rd. It doesn't matter. It just isn't important. It'll be... spelled that wrong. Okay. It's just not that important. Right? The same thing would be, right, if you're raking the leaves in your yard, right, and then there's an inch layer of leaves across the whole yard, if I went out there and picked up one leaf and threw it in a pile or took it away or whatever and got rid of it, does that even matter? Right? Because there's still thousands and thousands of leaves out there. It's not significant. It doesn't matter. So for most applications that don't require exact accuracy, it's not that big of a deal. However, floating points are not good if we want perfect accuracy. So I'm going to go back to, and we can now review again a little bit. We know the reason for this. Does your bank use floating point numbers to keep track of the decimal places in pennies? I bet you they don't. And why is that? Because banks need to be 100% accurate all the time. And a floating point is not accurate all the time, so you don't want to use it. And banks are 100% accurate most of the time. They do make mistakes. It's very, very rare, and in fact, it's more rare now with the computers. But it is possible. Okay. So we've talked about numbers and all kinds of different number systems. But how about letters? We could talk about some of the historical versions that are older than this. But when was this done? I'm not sure. Well, again, let's look it up because we can. ASCII. And we can go ahead. Well, that's nice. We'll look it up on Wikipedia because you know what? Wikipedia in class. That's just the way to go, right? American Standard Code for Information Exchange. We actually talked about them. No, we didn't talk about them. I'm sorry. We did not talk about them. Actually, let's look. Are they in? Oh, they changed their name. The United States Standard Institute. American National Standard. ANSI. And so we did talk about ANSI, the American National Standards Institute. That's the private nonprofit, right? And that was a member of the ISO, right, which is the International Standard, Organization of Standards. So, okay, so they've changed their names. But when they created this, they were called ASCII. Oh, no, I'm sorry. That's the name of the interchange here. And this picture is going to be kind of crummy. Oh, yeah, not good. I don't like that picture. So let's go to this extended table. I like this one better. Okay. So, reject whatever that says. Okay. There's some gaps in here. I don't like that table either. Let's go to images. This is maybe a better one. This is a good one here. Yeah, except for that has more to it. I don't want that. I just want the ASCII code. Come on now. Here we go. This is the classic one. Okay. So we can actually look at these numbers. It doesn't have it in binary, but that's okay. We could translate this. 1 would be 000001, and then F is 3 ones, and that's the unit separator. All of these that are in parentheses are white space. We can't see them. Some of them we're used to seeing: carriage return, vertical tab, space, escape. Well, we're not used to seeing that or using that. Those are the three main ones that we would normally see, but there are others in here as well, including actually one that's very important, end of transmission. There should be an end of file as well, end of medium, maybe that's it. Yeah, I think that's right. So, but for the most part, the first 32 of them are white space, right? They guarantee it to be a white space. So then we see space down through here, and then we've got the numbers, and then we've got some more punctuation. These are the more common pieces of punctuation. Although I guess the apostrophe is up here, the period is up here. Those are used more fairly often. But we've got, I don't know why they separated them. I think there's a reason why 1 or a 40 or a 0 is here and 1 is there. Anyways, then we get into starting at 65. Now 65 is kind of interesting, right? Because 64 is a base of 2. So 65 is a 1 with 6 zeros and then another 1. And that would be capital A. And then we go all the way down through Z with capitals. Oh, okay. And then it rounds out 1, 2, 3, 4, 5, 6. So that this one here is 2 1s followed by 3 zeros. No, 5 zeros. And then a single 1. And that's A. So we can actually make the transition from here to here by, it's exactly 32 numbers. And then we can go all the way down doing that. And then they put a bunch more things at the end. And 127, which is 8. Let's ASCII. Now, one of the reasons why ASCII was really important, really useful, or why not useful, but they came up with it. So one of the things that's important to note is in the early days of the computers, where were they being developed? Where were they primarily being developed? And that was in the United States and in England. And those are the two main places. And all the innovations were done. Almost all of them are done in the United States in the 60s and 70s. Then we start seeing some European countries to come in, and now we're starting to see much more parity across the world, which is good, right? But it was very centric in the United States, and they were very dominant as far as the development of computers. Which is why you see this. Now, the other thing that's a major advantage is this can be done with 8 bits. That's the largest number is, back here, was 127. And 127 maps out to 1, 2, 3, 4, 5, 6, 7, 8. And so I'm going to move this table to another page so I can look at it while I'm talking to you guys and have it up on the screen here. So let me just try doing my name. Or let's actually do, let's do one of my favorite people in the world, Mom. All right, so I look at capital M. Oh, I'm going to make those other two small. I'm not going to make them capital, so I'm going to make them small. So they'll be a little different. So if you have that open, we see capital M is 77 in decimal, or 4D in hex. All right, and then that's the M, and the little o. Little o is 111 or 6. Is that right? 6F. And then little m, and and little m is 109 or 6D. So we can say just in hex code this would be 4D 6F 6D. And if we do the actual transformation into binary, that's 4. D is 2 less than F, so it's 1, 1, 0, 1. And then 6, which is 0, 1, 1, 0. Yep. And then F, which is 4 ones, and then 6 again, which is 0, 1, 1, 0. And then D, which is 1, 1, 0, 1. So that, right there, spells mom. Feel free to share that with your mother, or you could share this with your mother here. I'm sure she will appreciate it, or maybe not. She might look at you like you're a little bit crazy, which maybe is true. You are taking a computer science class after all. That's okay. We'll revel in our craziness. It's all good. It's no problems. Everyone's weird in a different way, right? Not only is everybody weird in a different way, that's part of what makes us interesting. In fact, some of the most interesting people I know are absolutely crazy, weird, and in some way. Usually not in a bad way, which actually helps. Otherwise, you wouldn't be able to be in the same room as them, maybe. So, but everybody's going to be interesting in their own way, and we're taking computer science courses. So our way of being weird is the fact that we can look at these numbers and say, oh, well, that spells mom. Okay, well, if you can do that, you're better than me. But, fair enough. You can at least tell your mother that I said you should talk to her this week. So feel free to do that. I think it's still a good idea. All right. So we should all appreciate our mothers and our fathers as much as we can. It's a good thing. All right. So the problem with this is, though, there's actually a major problem. This is fine if you're just working in English. It has all the letters. But how about if you want to do a Spanish word that has an umlaut, or not umlaut, but I'm not even sure the nomenclature for it. Well, in German, right? If you want to do a German word that has an umlaut in it. I guess I studied German in high school, so I remembered that. It's one of the few things I remember from that class. Or a Spanish word. Or Arabic. Right? Those characters aren't even here. How do we do it? We can cheat some of it, right? But what they did is they came up with something called extended ASCII. Let's see if we can look at this one. Well, this one gets to 127, and everything's exactly the same. And then it says, oh, hey, the next group, extended codes. Oh, okay. And we've got this Y here, this AE, this Latin one, the cent sign, the pound sign. Well, that makes sense, I guess. There's a lot of different ones in here that are really obscure. But here we go, right? The Latin character with the grave, with an acute, with the circumflex, with the tilde, with a ring above. The AE, that's actually a different letter in Latin, AE together. And then we continue down through these, and some of these are used in different right? They're all used, for the most part, in European languages. Different ones. Lots of different stuff here. There, that's the double S in German. Lots of different stuff. But these are all pretty much still European languages. We still haven't even gotten to one like Russian. There's some letters in Russian that aren't on this list as well. They're just not there. Okay. Oh, the symbol for a euro? That's weird. That was probably a blank before and they added it in. Because the euro didn't exist when they first came up with this. So here's the cool part about it. Okay, let me go back here. This is 8 bits. So then they did an extended ASCII. Extended ASCII. That is 9 bits. We add one more bit, what happens? We double the number of characters. So this has 128 characters. This one has 256. Now, 256 possible characters, right? Because if we went back and looked here again, right, we see some of these are blank. Right? So this is blank. It's not used yet. They'll come up. Maybe something new will come along, like the euro symbol. And then there's these other spots that are blank as well. So there's very few blank spots. Most of them are then. Okay. That gives us a lot more language. It gives us more languages. It gives us a lot more ability to be able to do some of the words that we weren't going to be able to do. But there's still some characters that we know aren't there. Okay. A Unicode table. Oh, even has a heart right in the name. So this at the beginning, I don't even want to click on that, is the same, right? So these characters are all the same. Yeah. So this is right. Well, 3 zeros actually. Yeah. 3 zeros. This is what is going on here? I'm not exactly sure how this nomenclature works, but this is the first 16 characters, and then this is the next 16 characters. And then that's the space, and then we go down and we'll continue going down through them. Now, it was created in 1981. Part of the reason why it was created in 91 is because also we see none of the Japanese characters, none of the Chinese characters, none of them are here, not one. And so we have to account for those as well. So they realized that needed to happen as well. So also one of the other things that we go back to when we talk about ASCII or extended ASCII is those are computers that actually were very limited in their memory. So they had to make some sacrifices in order to kind of make them work. So, and as we move forward in time, computers got so that they were 16-bit computers. And so once you get to 16 bits, now you can do your Unicode. So Unicode is 16 bits. Back here. Unicode. it's 16 bits. So we doubled the number from here to here by just adding 1 bit. And this time we go from here to here, we add 7 bits. So then that would be, we double it 7 times. Just pretty significant. I think there's 16,000. Go back and look here. Does it say? How many possible characters there are? Well, let's get out your calculator. All right, go to scientific. 2 to the 16th power. 65,536. That's how many characters we've got. Oh, I even had it wrong. Imagine that. What was it, 536? Wrong one. 536, yeah. So that's the total number of possible characters that we can do with Unicode. And if I remember correctly, oh, it only shows us the first. Please load. Yeah, I don't care. So right, this. Oh, these are all those blank ones. They're white space. You can't see them. Then we go to the next line, and that's all the extended ASCII code, or it looks like it is. Maybe not exactly. Oh, some of it's here, actually. That's why. This is extended. So all the extended ASCII are all right here, actually. So we go to the next one, and these are more characters that we could use, more symbols. And we keep going, and keep going, and keep going, and keep going. Still haven't seen any of those. We do see like all kinds of different mathematical symbols even. Keep going. Ah, here's our Arabic characters. That's good. Bring those in. We've got languages that are gone, like cuneiform and some of that kind of stuff. And we're not going to see the pictures of those. More characters, more characters, more characters. We still haven't really gotten into any of the Chinese or Japanese characters. Or maybe we have. I just don't recognize them as readily. So, but there's a lot of stuff here. I think maybe this is cuneiform, actually. I'm not sure what cuneiform looks like exactly. Cuneiform is an interesting language. It was used very, 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 very long time ago. The Assyrians, I think. I think that's the right ones that used it. Boy, we can just keep going, can't we? What? There's a Unicode code for a little snowman picture, a sunny picture, or a partly cloudy, I mean. So that's actually pretty interesting. Oh, there's a little heart there. See, there we go. Oh, you can look that up. See, there you go. Does it say what that one is? It does. It's right there. That's our Unicode. It actually gives us an escape character, and this is actually really useful here. If you're ever going to run into this, you can actually get that to display by doing this /U2764. And if you're in a word processor, then it will actually put that heart in because that's the Unicode value. And then also in HTML, we've got this, which is a little bit different. Way to go. Oh, okay. So this is actually telling us what the different things are. Currency symbols. They're grouped together. Cyrillic, Greek, Hebrew, Latin, lines. math symbols, Roman numerals. Look at that, see? We don't have to even make them, we can put them in single characters. For some of them, right? Not for all of them. We've got 8, we've got 12, but we only have 13. Yeah. I guess they had to end at some point. And I don't actually see the Braille. Oh yeah, that's nice. So, and I'm not seeing the, how far does this go, huh? Well, I think this would go to, let's go to 64. Here we go. Here's some of those, not there. I think here we go. So we've got Chinese and Japanese character. I can't tell the difference between the two. Maybe somebody else can. But they're there. It's actually kind of cool. There's a little bit of a pattern there as we move through these. So actually, there's a lot of different ones, man. They're using up a lot of characters, but they need to, right? Because they have so many characters in their language. Wow. There's still more. Can we go to say 255 here? We just do that, jump right to it. Yeah. Oh, right, there we go. See, 255, that's the end. There's our last character right there. Not sure what it is, but almost at the end we have a question mark. So, how are these different? No, this is the end right here. That's the end. No, it's not. The end is F, is when this is like that. Yeah, that's the end. So that is the end one. So yeah, it looks like they redid some of the characters that we use in English. There's another name for them though. I don't remember that. Anyways, that gives us a little bit about Unicode. Unicode's actually pretty dang cool. And actually, I want to talk about one more thing. Because, so here's the thing. You're going to type a paper, say for this class. How many Unicode characters can you use? Well, you could certainly write it in the program that you use could save everything using Unicode. But it wouldn't necessarily have to. Okay, so it wouldn't necessarily have to, because there's a good chance that the majority of the characters that you use for this class would not be they'd just be in ASCII. So we could just save it in ASCII. Oh boy. We're about to run out of time. There's 2 other things I wanted to talk about. I guess I'm going to have to postpone that until Wednesday. Alright, so, okay. I lost track of time looking at Unicode characters. Alright, so, well, that happens. So I'm not necessarily going to adjust it, but we'll finish out chapter 2 on Wednesday. We have about 10 minutes left here, so. So, okay, most things would be in ASCII. Because they're in ASCII, that takes half the space to do an ASCII character, right? Because it's only 8 bits instead of 16, so it's half the space to save it on the disk. Now, in modern computers, I mean, because like a word processing file is tiny compared to, compared to some of the files we've got, how much storage we have. They're absolutely tiny, right? They're less than a kilobyte. They're really small. And for some of them. But if I had a big text, right, I had a several million words, it might be handy for me to use some kind of a system that would allow me to make it smaller, right, so that I used half the space. And that actually brings in one, actually, the book doesn't talk about it at all. And that is, what is it? UTF. Yeah, right there. That's it. UTF-8. Oh, I misspoke on Unicode. Sorry. Unicode is not 16 bits. Unicode is 32 bits. So it's 4 times as big. No, that's not right. Yeah, it's 32 bits. And this is not the right number. Wrong. Not correct. Nope, 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 nope. It's not that many. It's roughly 4 billion numbers. 4 billion? 1,000 million billion, yeah. So it's possible to have that many. We haven't used any of them yet. In fact, it's unlikely that we could ever use all of them. All right, so enter UTF. This might be 24 bits, which would still be 8 million. With it interest, let's just go Unicode here. Be nice if I got my stuff straight, huh? Yep, that's all nice. Uh, 16 bits per character, and more than significant for this purpose. So I was actually right in the first place. I did have it right. I did have it correct. Okay, 16 bits. All right. UTF-8. By the way, this is a great website. If you haven't used this website before, W3 Schools, amazing stuff. I highly recommend this website, W3 Schools. So if you see anything on W3 Schools, go ahead and click on that one. Okay, so what is this? How does it work? It's between 1 and 4 bits long. So it can represent any number, any character in the Unicode standard, and it's backwards compatible with ASCII. It's actually the preferred encoding for some of these things. Okay, I'll explain what that means. The first 120 using a single octet with the same binary value in ASCII. So most of the time it's just 1 bit. Or 1 byte, I'm sorry, 1 byte, or just those first 8 characters. And so it's just going to use ASCII code. So it's just going to look at 8, do it, look at 8, do it, look at 8, do it. Okay. However, what it does is this is, it's not really, well, this is, why is it not saying it? So it signals whether or not it's short or it assumes short always. And then if a certain bit is flipped or certain character is displayed in that first slot, then what happens is it says, aha, this is different. And so then it just defaults. I'm not sure. I think what it does is it says how many bits there are that are significant. So then it will increase the amount of space that we have for that character. So then it comes along, it just keeps going. It says, so this is ASCII, this is ASCII, this is ASCII, this is ASCII. And then it gets signaled, hey, this is not ASCII. So then it changes its thing for that one that's longer. So then if you have a few characters in there that are Unicode, then it could extend out for those. And this is what we use for almost everything. There is a UTF-8 and a UTF-16, I guess. So, by the way, and this is actually kind of interesting, is I've actually used UTF-8 in my work. So I work for. I told you guys, right? Yeah, at the beginning, right? I work for a consulting company out of Wayzata that rents me out, as it were, to Thomson Reuters. So about 40 hours of my week is put into Thomson Reuters, and we're working on a website. So in one of the cases, we actually ran into a problem where we had to, because I'm doing testing, and so we had to convert it and force it to use UTF-8 because it wasn't doing that properly. So it was an interesting problem. And I don't remember the whole context of it, but it was something that did come up in my actual regular job. I have not been able to find an AD that lists the specific bytes. I only see storage devices for sale listing the rounded number of bytes. Oh no! That's problematic, isn't it? Well, okay. That's great that you've put that question here for us. So what you should do then is, if you can't find an ad. Yep, yeah, ad or advertisement. Okay, yep. Okay, so if you can't find an ad, so spend some time looking for it. If you can't, explain what's going on in that, right? Listen, I couldn't find one that gave me the exact number, and so I can't do this. But try to answer the questions to your best of your abilities, without finding that ad. So do your best. See what you can find. And then basically report that in your answer. That's perfectly honest. You're giving me an honest effort, and that's all I'm asking for, right? I'm asking for you guys to give me your best honest effort. So is that good? Hopefully that answers your question. Let me look at the wording on that. Look at the details of the ad and find the exact, not rounded amount of storage in bytes. Yeah, it's interesting how they do that. They don't give you the exact number anymore, because you're not going to be able to find the difference, and that's going to be okay, right? You simply cannot find that, and that would be accuracy, not precision, accuracy. Right, because if it was different. Okay. All right, good deal. All right, so this, let me just say, this is one byte to 4 bytes. Okay, that's it. And it uses a signal to do that. Probably not something I'm going to test you on, but it's something that might be really interesting to know in the real world because you might use it. All right, well, I think we're past time and we're actually over time. So I'll call that a night and a weekend, and it's a 3-day weekend, so there's no lecture or anything on Monday. So that's a good thing, right? We do 2 weeks and 2 good weeks, and then Monday happens, and Labor Day happens. Hey, if you're close enough to the state fair, I heard the state fair is great. One of my coworkers was there yesterday, and he said the crowds weren't too bad. So feel free to go to the state fair, unless you're watching this in another week, in which case then you're probably have already missed the boat on that. So although it might be more busy over the weekend. So if you get a chance, go. I hear it's really good this year, so that's what I've heard. Of course, I've never been to the state fair in Minnesota, so that fair enough. All right, that's it. I'll talk to you guys again next week, and hopefully then, yeah, make sure you get your assignments done in to me by tomorrow at 5:00. All right, thank you, and